Right. Welcome to ACL 23 quarterfinals. Congrats on making it this far. You have 30 minutes, and let me share the share pad link with you. Give me a second.
Okay.
All right. So in the chat window, you should be able to get the link. Did you get it? Nice. Oh, nice. So it's coming up.
Yes.
In that case, I'll copy paste the question description for you, and then from that point on, your timer will
Okay.
start. All right. Best of luck.
Okay. The subset should contain more than two elements. If I have only one element, is it possible? How can we create a pair? Okay.
Yes, so basically, if we have one element 4, the answer would also be 4. So I guess it goes without saying that it
Okay.
can form a pair with itself.
Okay, this is my implementation. I guess it works, but I don't know if there is another corner cases other than the possible two options described in the above.
Yes, maybe we can go over your code and what it does in the next 4 minutes.
What?
Maybe you can explain your code,
Okay.
which section,
Okay.
what it does.
Okay. Okay. So I have two possible options. The first option is I starting from 1 up to the square root. First, I find the square root. So in that case, I add all the numbers that is found in that value. For example, in 1 means 1 square, 2 square, 3 square, 4 square, which indicates the let's like index is equal to I times I, but it's index based one based index, so I should decrement by 1. So I should add all that values in the answer. I have another array which stores the different complete subsets, say ans. So I should the first all the perfect numbers should be stored in the first way. Then I should implement. I implemented the next possible ways, that is starting from 2, 3, 4 for all numbers, which is the odd number of their power. So starting from 2 up to the square root number. So initially the index starting from that number I. The first number is itself, for example, it's 2. The next number is 2 times the square of the number. For example, the difference between those numbers is 4 because if we divide 2 cube by 2, it gives 4. If we divide to the power of 5 by 2 cube, it's also give 2 square. So in that case, I should add the numbers at the given index, array of index minus 1, and the index should be updated by I square, because in every case we should add 2 powers in the power 2. So finally, in this case, it solved all the numbers. So the last result should be the maximum of the answers. Maybe there are a maximum number from the given array. So I should the max of those.
I see. Makes sense. If you scroll down a little bit, I have pasted another test case. Let's maybe test run it for that one. And if you have another edge case that you want to try it on, feel free to do
Okay.
so before we finalize the interview.
$19. Is it a 19?
Yes, yes, it should be 19.
Okay.
All right.
Okay.
So you
So
have 2 more minutes if you want to discuss anything or add edge cases.
okay,
Yes.
the time complexity is of n because uh, every number is categorized into one of the complete subset. So each number is iterated 1 times. Even if I have a nested loop, even if I have a nested loop, but it takes every number is inserted in one of the completion subset, and the space complexity also of 1. This approach, it's all about.
All right. Corey, good job. I think we're just on time. So for our watchers that might be watching this from YouTube, they might be curious as to if your code passed or not. So you can stop sharing your screen. I can share mine, and then
Okay.
we can submit it. Mukerem. Can you see my screen? You can, right?
Yes.
Awesome. All right. So it's passing for the test cases, and we're about to submit. Okay. So you have a
There is
wrong
an
answer, and it seems there are some cases that we didn't took
okay.
care
In
of.
which test case?
It's a long one, so your output is 59, but it should have been 64 basically, and you
Okay.
passed 590 test cases, which is good. A
Oh,
substantial amount.
okay.
Yes. But good job. It was a pleasure seeing you trying to tackle the problem. Uh,
Okay.
yes. So good job, and I'll
Okay.
interview your next contender, and the results should be in the afternoon.
Okay. Thank you.
All right. Have a good rest of your day. Bye.
Thank you.
Okay, thank you.
Cool.
Mm,
So I've shared with you a link for a shortcut. You should be able to find it in the chat window.
okay. Is my screen visible?
Yes, I can see it. I'm going to be
Uh,
pasting the question for you. You can see it now, right?
yes, I can see it.
Awesome. So your timer starts now. Good luck.
Can I take a few minutes to read the question?
Sure, take your time.
The index. Okay. So the question states that we are provided an array of n integers, and in these integers, we're supposed to find a subset of indices in which the indexes should be complete, which state that an index is supposed and subset is said complete if the product of every pair of its elements is a perfect square. And we're supposed to find the maximum element sum. Is my understanding of the question correct?
Yes, a maximum element sum of a complete subset, I guess.
Okay. Now, to start with the brute force approach, we can of course check every scenario. Say that since we're going to be asked here a subset, not a subsequence, we can go in any order we want. We can start from one, and we can iterate through every element and check if that element is a perfect square. And if that element is a perfect square, we can just add it to that to the index of one. Right.
I
So
see.
we must first define the indices, right? So in this case of one here, we should multiply to any element that isn't a number, and that is every element that can be multiplied by one. In addition to multiply plus one, it should be a perfect square. And for every number we get, which can be complete with one, we will also try to find for numbers that complete for it. And we're then going to find the intersection between the numbers that complete one and the numbers that complete each number in one. Is what I'm trying to say clear?
Yeah, so basically what I understood was the brute force would be we would explore every index and its matchups basically with
Yes.
which indices it would give us a product of perfect square.
Yes.
Okay.
The constraints of this problem has not been provided. Am I
Yes.
just supposed to find the optimal answer?
No, I can give it to you. So basically the lengths of the namsari can go from 1 up to 10 raised to 4. So at worst case it would be 10,000 the lengths.
I'm sorry, I didn't hear. 10 raised to what?
10 raised to 4. 4.
4. Okay,
Yes.
so an overin approach.
And
Okay.
the values of the array can range from 1 up to 10 raised to 9. So basically they range in
Okay.
between 1 and a billion. Yes.
Okay. So it will be 10 to the power 4. Let's take an overin approach here now.
Like what's the time complexity of your brute force approach?
So in worst case, we will have to check each element against every other element and set it. And then again, we have to go. So the worst case will be n square, an n square approach, since we will have to check each number against each number. In addition to that, we will have to have a second for loop. We're checking each of the elements. A for loop, a double loop will have an of n square time complexity, and since this is 10 to 4, this is not a possible solution.
I see. Thank you for clarifying that, Yabsera. Proceed.
So sorry. So we could have element of, maybe we can start with first having a set of all possible perfect pairs. If we add all possible perfect squares, maybe the way we can check whether each of them is there. So I mean a little bit of a prefix sum approach. Let's see if we can, but we should check if that's about right. Okay. It's a little difficult. 8, 7. So we are at so each index we can check the other indexes there or not. For the other index is a passable element, then we need to find it. So if we had, let's say, set here where we could have the maximum here is so by multiplying this element we can get a maximum of 81. So all perfect squares still 81. Basically that's what we can. So we can get to a maximum. We should find the maximum of the biggest sites. In this case it would be like since the 10 raised to what, we could get a set of 10 to the power of 9, which is a possible solution. If we just add set, take a bit of n, so don't even be of n. So the answer should be like 2 times 8, 1 times 4 perfect squares. 4, 9. That's right. So we need to find 2 elements in that is solvable to that. Okay. So let's lay upon the solution, right? So if we had with 1, and we go to 9 amounts. For 1, let's check. For 2, we could find out how many there are. For 3, we can find out. For 5, for 6, for 7. This will create our set. Then for each value of that, we should have to create an element of it, which is difficult. So we might have 1 approach. Then for 1, we would have 4, since 9 is our maximum. 8 is our maximum. So 2, 9. For 2 we can just 8, I guess. We have 8, and for none of them we will. So let's say we had, if we had an example of 9 here, we need to find an element with 4 that would also be possible with 9. Like so. This is difficult since it's allowed to go anyway. Dynamic approach. Dynamic approach. Even if we found the elements there, so so eight start with index 1 and index 9. If okay, let's think of maybe a dynamic approach type of thing, a dynamic programming approach. So maybe if you had an index, maybe index and a flag here, let's just have an index and a flag. So for each index, we can choose to take it, or we can not choose not to take it. Can we note this one? No, I don't think so. Okay, let's take it. Okay, maybe let's think about the consider the full brute force approach here. So let's create an example here. What would it be? The sum of 4. Let's add more numbers to 4. 4 times what could give it, like 4 times 8, 32, 25, something like that. So since we can't repeat that number itself, we're going to have to find a number that mimics that. Right, so for instance, 1 times every modulus number here is available, then every takeable, then for every parent's perfect. Set of numbers is complete if a product of every parent. So we need to make sure here is the index. Those index multipliers should provide another number is the whole point. So how much is left in here is another way we can check it. If we had a set of all the indexes, maybe if we iterate through every number and check if okay, that's difficult. Still would be off elsewhere, right? If you had maybe a set of, so maybe let's consider the brute force approach and we can get a better solution. So if we have the value of nums which are perfect squares, so in this state we have 8, so we can, if we had 8, since we can multiply 8 times 8, this times this maybe, so 8, 7, what then the nearest sequence that's bigger than 8, right? So here at 16, can't have 9. Have made it at 9 here, but we should the double of it, which is less than the double of it. So here our perfect will be 4 and 16 only. So maybe if we iterate, and we have to check if every multiplication is in here. But that wouldn't solve the problem. So let's say we created a dictionary here, and the dictionary will have, for instance, it would have 1 would give times 4, and 2 would give us 8. So maybe if for every other, we should check that if it's in here too. So that would give us like a graph type of thing, right? So that means for every element. Okay. Then we iterate through the second loop would be iteration through the second loop, and we would check if for possible answer. So we can take for 4. if 4 and set. So if 4 being the set, then if 4 is in the set, then we have to check in for force elements. And if force all elements, okay, this is confusing. Okay. Yes. Brooke, how much time do I have?
We just passed the 16 minutes bar, so you would have 14 minutes left. But
Okay, thank you.
so for two indices to get multiplied and to give you a perfect square number, what do they have to be? Like,
For to be multiplied, they.
yeah.
I'm sorry.
Yes. So, like the question for a subset to be a complete subset, every pair that you can form, they have to give you a product of perfect squares, right?
Yes.
So let's just single out two numbers or two indices, and then for them to get multiplied and give you a perfect square, in what way can you represent them?
Okay, to be a perfect square. Like 1 times any number, they should be multiplied. I mean, if you go like maybe prime factorization.
Let's say a times b gives you a perfect number, right?
Yes.
And how can you represent a times b even further? Like, can you represent it, for example, a times t, oh no, a times c times b? Can we do that?
Okay. Yes. So yeah, like in case of they should be since there will be an error, one of them should be divided by a given number, and one should be added by a given number. Yes, we can do that. Okay, but we would have to then if we did that, we would a times so for some number when multiply times that number, and when another similar number is divided by that same number, we should be provided with the term for instance, in this case, it should be 1 times 2 and 2 times 1. Yes, we can do that.
Yes, for
So
example, for the number 2, which other numbers would give you a perfect square when they get multiplied with 2?
for the number 2, which other number? So for example, if we say like by 4, when multiplied plus 4, that would is 2 times 4. I mean 2 times 2 should times 8 times 1 over 2 would be technically the. So maybe if we if we had a set here, let's say we had a dictionary here, maybe a dictionary. So for each element 10, but we'd have to check each element in here, right? Since the dividend, we can check if the dividend is in there. So for each number, if let's say we had a set, maybe, and a set for each element for each element multiplied by a given element, we should check if it's in. But what element do we go? So we can check to what the element would be the maximum. If the difference between maximum and the minimum is large, we might have to multiply it with a lot of numbers, which would again mess up the complexity. Once you think about it.
Like going back to the number 2, so other numbers that give you a perfect square when they get multiplied with 2 are, for example, 8, 16, right? So 16 times 2, actually, no. 2 times 32 would give you a perfect square, right? 64.
Yes. Okay.
Also 2 times 8 would give you 16, which is also another perfect square. So these numbers, which are 8 and
Yeah.
32, what's different about them in relation to 2 compared to other numbers?
There are powers of 2 which could be added. Okay, I think
Not
I
only,
get what you're trying to say. Hello?
yes, so not only power of 2. So if you take, if you divide them by 2, they would also give you what? So for example, if you
If
divide
they,
8 by 2, it would give you 4, right? If you divide
yeah,
32 by 2, it would also give you 16, which are also what? Perfect squares. Does that make sense?
yes. If you multiply a perfect square with another perfect square, they would always provide you a perfect square.
Exactly. So now for an index to find it's another half to give you like a product of perfect square. It should what?
So for another product to give you, it should be multiplications of perfect squares.
Perfect squares by that number, right? For example, 4 times 2,
Yeah,
8, or
yeah,
16 times 2, 32.
yes. So we need to multiply it by multiplying it. We need to create that. So for instance, in two, for two elements, any number that half of all elements should work by should be possible by 2, or same for 3. So we go maybe 8, 32, like that. So these are that should work with 2. They should be they should be multiplied by. So the next element should be 32 times 4, the square of that element. Okay, I think I get. So for 3 possible article 3 would be maybe 81. 81 divided by 3 would be 60, right? 81 divided by
27, I guess. 8 divided by 0.
so
Mm-hmm.
okay. So it will be 27. Any multiplication of any number that you can multiply by 9 would always find you if you multiply that element by 6, I guess the double of that element, you can always find your set. So the set that is equivalent with 2. But the problem here with that would be 1832. Would the 1832 be, or the 1832 will also be perfect pairs of each other? Then the power of 2 would be add up. Okay, so for each indexes, we need to find for so we can do this with all functions. So for each indexes, we need to find a number, the multiplied number. For instance, for 1 it would be 4, for 2 would be 8, the closest number that would provide you the set, and we just have to keep on multiplying it, and we would find a suitable set. And we just have to do this for prime numbers as well. But we have to do this for all prime numbers. For example, 17 can't help you find another number. Okay, so in this example, we could say we start from 1. For each element, for each numbers in the index, we check if 1 is less than the n, right? We
Mm-hmm.
add that number, then we add next number. We just multiply that number times 2. And we check if the number is less than n. If that number is less than n, then we can be guaranteed that it's say if that's it, we just have to, we can add it to our element. Okay, so let's start with our initial. So let's start here. Let's say we had a, yeah, we can have a max here. If we had a max of 0, and we start from index of 1, and any number that's so when start is 1, actually any number that's a square could work with 1.
Mm-hmm.
You don't have to think of the multiplication. So so for 6, it's for 3, it is a number that finding the perfect square times 6 will always get you the result. So for 1, 4, and the next element would have to be 9. So for 1, it would be a different scenario. But let's say for 1, it might be an edge case. For 2, we will have to
By the way, if I give you just an array with the element 4, the answer would be 4.
yeah,
Okay, just to make
for
sure.
1, yeah, okay.
Yes. And you have roughly like 4 minutes left. Yeah.
4.
Yes, let's say 5 minutes for the introductions.
Okay. Can I begin with the implementation?
Yeah, sure.
If we max is equal to 0, set and just take that for each element of I. So for 2, if 2 right, so we need to first find the perfect square element. So the perfect square that's bigger than that element is we need to so for 2, for I if element is I, so we have to find the element closest to it. Okay, if we have an array of perfect squares, how can we? Okay, let's say perfect. So append of n times n. Just create an element n here that allows to have the perfect. Then we say our first value will be the numbers at the state. So we go out of array of at I, then let's say pose is equal to basic left from perfect. Basic left perfect. Let's say basic left perfect, and we're supposed to find basic left perfect, and we're so before one need the element that would be, so we take I, and we should also make this from 1 plus so we should check where that element lie in here, and the position of that element would be the closest nearest square, so that would be our number. I plus 1 suppose is less than n, we just have to add next here. Plus r at the position. So then we just have to multiply those times equal to 2 times then max so we first create an array of every element. We create an array of the perfects, then we'll hold n, then for every element in that range or in the size of n, we start with the initial value at array of 1, then try to find the nearest perfect to that I, and we get the position of that if that position is less than n, So if it's technically less than n, we just add that element and multiply that 2 times I to that element. Yeah, for 1. And if it is in case the element, let's also start with the max as. In case of this, for 1, we just have to find perfect. So for
All right, Yabsera, it seems like we're on time.
max is equal to 0.
Yes. So
For
last minute touch in the next 30 seconds and we will stop the interview.
if I perfect imperfect, and we have max that's equal to I guess the area of hello.
Yes. Can you hear me, Yabsera?
Hello.
Yabsera, can you not hear me? Hello.
Yes, I can hear.
Okay. Awesome. Yes, so I was saying we are on time and we have to stop the interview here. But for our
Okay.
viewers that are watching this from YouTube, possibly, they might be wondering if your code actually works or not. So let me copy paste your code. Let me share my screen in the next 2 minutes and then give me a second.
Okay.
Okay. So, guess this can be inside R. Let's run your code. I guess it can be R. Okay, so we have an index out of bounds issue. So it seems, but I guess since we were on time, you didn't have enough time to debug your code, which is fine, and it happens more than often. But thank you, Yabsera. This was great. I enjoyed our interview. So you are going against Mukerem, and the result should be in the afternoon. Wish you the best of luck. Thank you.
Okay.
All right.
Thank you.
Have a good one. Bye.
Bye. Thank you.